Hey everybody, this is a remake of our video for problem 13 from the first Superquiz, where I made a small mistake when I set up, the improper integral was fine, but the way I evaluated it was a little off. So let's try this again. So again, we are reminded that velocity is the rate of change of position, right? So the velocity function, v of t, is the derivative, right? Every time you see rate of change, you should think derivative. So the velocity is the derivative of position. On the other hand, that means that if you anti-differentiate, right? If I anti-differentiate velocity, I should get position back. So we're given, actually, the velocity function, right? So the amount of velocity of whatever body is given by 1 over t squared plus 1. And we want to compute the total distance the body moves starting from 1. And we're given a hint to set up an improper integral, and that's because when we know that the velocity is given by v, then the amount of position moved will be given by the area under the curve corresponding to v. And we can get the area under the curve by integrating v. So we know that the total distance is going to be given by, we're going to integrate, well, it says starting at 1. And then, well, where do we stop? Well, it doesn't actually tell us where to stop, right? We just want the total distance that the body moves. And so without knowing when it's going to stop, or even if it does stop, we just say, well, we'll go off to infinity, right? That includes all time. And in fact, looking at the velocity function, we can see that as t increases, the numerator, well, is constant, but the denominator grows to infinity. So the velocity goes to 0, right? But it never actually gets to 0. So this body will never actually stop moving. And so to compute the total distance, it really makes sense. We have to integrate all the way to infinity. And we just have to integrate the velocity function, right? So 1 over t squared plus 1 dt. Okay, now, if we call this function f prime of t, right, so f prime of t, that's our velocity function, is 1 over t squared plus 1, then f of t is the arctan of t. So to compute this improper integral, we need to compute now the arctan at infinity minus the arctan at 1. So in the previous video, I had mistakenly converted this 1 into a 0. Right? There's no good reason for that. It was just an oversight. Okay. So what about the arctan of infinity? Well, let's draw a graph of the tangent function. So the tangent function, remember, is a periodic function. And a period has length pi, and it goes between, say, the first period in the middle, right, goes between negative pi over 2 and pi over 2. And the graph looks a little something, like that. Okay, so this is a graph of tangent of t. So what we see is that as the input, t, approaches pi over 2, the value of the function, tangent of t, goes to infinity. The arctangent, that's where you read the graph backward, right? So the arctangent, the inputs come along the y-axis, and the outputs come along the x-axis. So if I want to know what the arctan of infinity is, that is really, as t goes to infinity, what happens to the arctan? Well, as we go to infinity, and this, right, this is going to infinity now for the arctan, I look over and I see, well, what is the graph getting closer to along the x-axis, or the t-axis? And it's getting closer to pi over 2, right? So as I go off to infinity here, my t must be getting closer to pi over 2, and so that's what the arctan of infinity is. Arctan of 1, well, you need to know when do you actually get a tangent of 1. That means the sine and the cosine are both equal to each other, and that happens at pi over 4. So this is pi over 2 minus pi over 4, which is equal to pi over 4. So the total distance the body will move, starting from time equals 1, will be pi over 4.